All right, hi everyone, BC Calcs. This is Miss Yam, and this screencast is going to help with the summation clarification, summation confusion that I felt and heard from some of you last Friday. I will tell you that I did talk to Mr. Logue, and I did say, your kids from AB last year were not wowed by the limit of the Riemann sum, to which he said, well, we never showed them summation notation. And I said, what? So what did you make them do? And then he said, well, we just made them count up the areas of the rectangles. And so that helps clarify why it is that I got some relatively blank stares from the likes of our AB veterans, Shreya, Meghana, Walter, and Kate. And I will say also it was pretty funny. I think, I forget what point it was in the class on Friday, when I was saying that the summation of from k equals 1 to n of k squared equals n times n plus 1 times 2n plus 1 over 6. And I was convinced you had all seen this because Nancy had said, oh no, that equals n times n plus 1 times 2n plus 1 over 6. I think you'll all laugh when Shreya looked at me. I don't know if you all heard it. She said, Miss Yam, please do not use Nancy as a benchmark for what we know. And it was a really funny moment. But I will explain this as well in this screencast. Okay, first thing with summation notation, everyone. Gary, you had asked, the question about K versus N. So there were some questions that make it very clear to me that I think just basic summation notation, there's just some foundational points of confusion. So this screencast should clear all that up. When we have a summation here, okay, the variable that is changing integrally is K, okay? K, and the thing is, whether this is K or M or P, it doesn't have to be K. K just happens to be the most commonly used letter, just like with functions of X. It doesn't have to be X. X just happens to be most common. The K value that you start is the lower limit of summation. The K value that you end at is the upper limit of summation, and K varies integrally. This here is called the summand. And in the summand, wherever the index of summation, that's the variable of the sum, so to speak, that is what is changing integrally from 1 to 4. This summation means add up, okay? You're adding up terms. So you'll see here the first term is the summand with k equals 1. This is k equals 1, okay? This is the term when k equals 2. Here is the term when k equals 3. Here is the term when k equals 4. Terms. These are individual terms, and we are always adding them up. The addition is implied in this summation notation, okay? 99% of the time, and what's funny is I'm sitting here with Nina saying, say hi, Nina.
Hi.
Nina's in pre-cal, and we just finished a unit on summation. And I remember it's so funny because I actually think you all have seen this in some capacity. You may have just forgotten it, especially if you went Kate, I'm thinking of you. If you went TFA, AB, you probably haven't seen summations for actually 2 years. So, okay, the point is I understand where some of the confusion is coming from now. Okay, now here's the thing. Does K always have to start at 1? No, it does not. Starting at 1, though, offers some convenience. The convenience it offers is that the first term always corresponds to K equals 1. I mean, I could do this and start a sum at k equals 3 and end it at 5. And let's say my summand now is 3k. What you have to realize is that when you do not start at k equals 1, you have to make the mental adjustment. You're starting at k equals 3, so the first term is 3 times 3 plus 3 times 4 plus 3 times 5. The point here is that when you don't start at k equals 1, if someone asks you what is the first term, well, you have to state the first term occurs at k equals 3. And my hand just wrote the wrong thing, okay? So for convenience sake, it's nice to start at k equals 1. The other thing that's nice about starting at k equals 1 is that if you look at the upper limit of summation, that number, if k equals 1, this number will always correspond to the number of terms you're adding. So do you see here we go from k equals 1 to 4? Well, there are 4 terms, 1, 2, 3, 4. If you start at 3 and you end at 5, for example, you can't just quickly say, oh, there are 5 terms I'm adding. Here, there are only 3 terms, okay? So if you don't start at k equals 1, you have to adjust and say, oh, it's the upper limit minus the lower limit plus 1, all right? So starting at k equals 1 is incredibly convenient. What we did a lot of work with in my pre-cal class a couple weeks ago actually was rewriting a sum that does not start at 1, rewriting it to start at 1, where the summation or the sum of those 3 terms is the same. So an exercise we worked on was express this same sum of 3 terms, but now I want the summation to start at k equals 1. And what happens here, as you might guess, is that, well, you have to adjust the summand, and you also have to adjust the upper limit of summation. So here, the summand of 3k, when I started k equals 3, it has to become now 3 times k plus 2. And you'll notice if I change the summand this way, my first term is 3 times 3, right? Which is the same as above. And the second term is 3 times 4, which is the same, et cetera, et cetera. The upper limit of summation then would become 3. So again, the point is that having a summation that starts at 1 is just convenient in a number of respects. The issue yesterday, I think this is Geary said, K versus N, that's kind of throwing me. All right, well, let's see. Again, let's just pretend here that I have something like this to 22, and I have, okay, so let's take a look at this for a minute. So this is a summation from k equals 1 to 22 of 2mk. If I were to expand out this sum, I would have 2m times 1 plus 2m times 2 plus 2m times 3, so etc. All right? The very last term of this sum would be 2m times 22. So here's the thing. When we start at k equals 1, we notice that the upper limit of summation will equal the number of terms we are adding up. So Geary, what I was saying was, what happens if we change the upper limit of summation? I was calling that number n, okay? So let's take a look at this one. K equals 1 to n of 2mk. Well, this is going to equal 2m times 1 plus 2m times 2 plus 2m times 3 plus, now the very last term is going to be 2m times n, okay? So I was using n in our class as the number of terms we are adding. When k equals 1, what's convenient is that the upper limit of summation then equals the number of, and in our work, it was the number of rectangular subintervals, okay? The number of rectangular subintervals, okay? And in our case, the number of terms in our sum, it was the number of rectangles areas, right? I'll write that down, or the number of terms being added. Okay, that's the difference between K and M. Something I want to make you aware of is if we look at this summand, the summand is the argument of the sum. And if there is a constant factor that I can factor out, and you can probably see it here, right? K is that which is changing. The 2M is not. So this factor I can pull through. I can rewrite this as 2m times the summation from k equals 1 to 22 of k, because as k increases, right, k is changing. Look at the terms here. K is changing this, but of all these terms, the 2m is a constant factor. Now, the same thing is true here, because look, from k equals 1 to n, do you see the terms? 2m times 1, 2m times 2, 2m times 3, 2m times n. Again, the 2m can be factored out. So here I could factor the 2m out. And that's the same sum. Now, where things tend to get a little bit confusing is this. let's say I have the summation from k equals 1 to n, let's do this, of k over n times n squared plus 1. Okay, so if I look at this, this is where my substituting and factoring out, I think, threw you a little bit. Well, let's just do a couple of things. Let's write out the first few terms of this sum. Okay, when k equals 1, I have 1 over n times n squared plus 1, plus 2 over n times n squared plus 1, plus 3 over n times n squared plus 1, and so on and so forth, okay? The very last term is going to be n over n times n squared plus 1. If you look at all of these terms, do you notice what you can factor out? All of these terms have in common the n squared plus 1 all over n squared plus 1 all over n squared plus 1 over n squared plus 1 over n, because that which is changing integrally, we're looking at the k. So this sum, I could rewrite this as n squared plus 1 all over n times, right, the whole thing times the summation from k equals 1 to n of just k. All right, so again, don't let the k and the n throw you. K and n, when you're just given something like this, it could look intimidating. But remember, k is what's changing integrally. N is the number of terms we're adding. And if you're ever in doubt, write a few terms out so you can see what the constant factor is. The reason why this is so important is because we looked at limits then. See, now I'm going to do this. Well, we want the limit as the number of terms approaches infinity. The limit as n approaches positive infinity of all of this, n squared plus 1 all over n, times the summation from k equals 1 to n of k. All right? Here is where I very quickly, and I think this kind of just made you go bananas, largely because it was, I think, in all honesty, I think a lot of it was because it was just last period Friday. But your question was, where on earth did my formula come from? Let's come over here. Okay, I'll do a quick derivation of this one. The summation from k equals 1, let's just say n is 100 of k, right? This sum is going to look like this. 1 plus 2 plus 3, plus 4, plus all the way through. Let's just take the last 4 terms, plus 97, plus 98, plus 99, plus 100. Okay? This is the derivation part. This is a derivation shortcut I showed my class last year. You'll notice that 100 plus 1 equals 101. 2 plus 99 equals 101. 3 plus 98 equals 101. And in fact, how many pairs of 101 are there? There's going to be 50. So really, this sum, which is here, this just equals 101 times 50, okay? And you'll notice that, let's see, I let n equal 100, right? N equals 100. This number here is just n plus 1, okay? This number here is just n divided by 2. So that is why you saw yesterday, right? The summation from k equals 1 to n, right? Here, n is 100. N could be 2,000. N could be 5,000. The summation from k equals 1 to n of k, which is just 1 plus 2 plus 3, so on and so forth, is just the number of terms you're adding right here times the number of terms you're adding plus 1, all divided by 2. This is a nice generalization. This equals, now you have it, this equals a summation from k equals 1 to n of k. All right? And now what I do is I go back and I now know what this summation equals in terms of n. So this becomes this. The limit as n approaches positive infinity of n squared plus 1 over n, right? This is still waiting in the wings, multiplied by this summation, which equals right there, n times n plus 1 all over 2. Now let's just play with what this limit would equal. What would this limit equal, everyone? As n approaches positive infinity, you don't have to multiply everything out in the numerator, though you can if you want to. But when you look at this, if I were to multiply this out, it's a rational function where n is approaching positive infinity. So all I care about are the dominant terms. The numerator is going to equal n to the fourth with some lesser degree terms, all divided by 2n. So as n approaches positive infinity, in this case, this limit is going to approach positive infinity, or we say the limit does not exist. Okay? So that hopefully will clarify all this stuff about sums and limits. Let's see. You had a question, I think one of you said, where did this come from? How did I know what this equals? The summation from k equals 1 to n of not k, but of k squared, right? Like, how did I know this is called, by the way, this here is called like the explicit formula for this sum. Like, how did I get the explicit formula for the summation from k equals 1 to n of k squared? Okay, well, let me show you. So to prove this, okay, to prove this outcome, to prove that the summation from k equals 1 to n of k squared just equals this, we have to prove this by a method of proof called induction. Here's the thing. If you don't care about the proof and you don't want to watch it, what I'd say is you could stop now, all right? Because the proof by induction is going to take about a solid 10 minutes. No offense if you don't want to watch the proof, but I will say you do need to know this, all right? So you do have to know this is the outcome, all right? So whether or not you want to know why, that's up to you. I'm going to now go into the proof by induction. So induction is a method of proof, is a way of proving it's called a lemma actually, but okay. Induction is a method of proof whereby 3 steps have to be followed, okay? You show that which you are proving, you show that it's true for a discrete, and I'm going to put in quotes here, a discrete first case. The second part is you assume your principle is true for an arbitrary case. And then the third final step is that you then prove true for your arbitrary case plus 1. Okay, what does this mean? So really, let's walk through it. 3 critical steps in proof by induction. It's show, assume, and then prove. So here's what we're going to do. We're going to use proof by induction to show that this is indeed the explicit formula for summation from k equals 1 to n of k squared. Step 1, we're going to show true. I'm going to show this is true for a discrete first case. So I'm going to show true for when n equals 1. Well, let's see. The summation from k equals 1 to 1 of k squared should just equal 1 squared, which equals 1. Does the explicit formula when n equals 1 equals 1? Well, let's check. 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. This does in fact equal 2 times 3 over 6, which equals 1. So we have showed this is true for when n equals 1. All right. Second step, we're going to assume that it's true for an arbitrary case. So I'm going to assume this is true for when n equals some arbitrary case. Arbitrary case here is a general, that's a general phrase for whatever the case may be. Here what we're trying to prove is that this outcome is true for all n, right? So I'm showing true for when n equals 1. I'm going to assume true for when n equals some arbitrary case q. So the summation, I'm going to assume that when the summation from k equals 1 to q of k squared, this should equal, again, I'm assuming this is true. This should equal what, everyone? Now watch your n's, k's, and q's. This should equal q times q plus 1 times 2q plus 1 all over 6. So I have now made that assumption, all right? Again, watch, see, make sure you're clear as to where all the n's and p's and q's went. All right. Here is the third step. The third step is pretty much the critical step from proof by induction. I have to now prove this is true for when, look what it says, the arbitrary case plus 1 is the value for n. I have to prove true for when n equals the arbitrary case plus 1. All right, so I have to now prove that the summation from k equals 1 to q plus 1 of k squared, I should have to prove that this equals what, everyone? I have to prove that this will equal, be careful, I'm plugging q plus 1 in for n. So it's going to be q plus 1 times q plus 2 times 2 times q plus 1 plus 1. So 2 times q plus 1 plus 1 all over 6, okay? So this is the proof. This is what I have to prove. Be careful again. Notice how my upper limit of summation, this q plus 1, has to be subbed in for n here, okay? N, n, and n. All right, here's my proof. Here we go. Well, let's see. The course of my proof, the proof will always kind of look like this. When you're proving true for the q plus first case, we're inevitably going to use our assumption from step 2. So this here is equal to, now watch, this equals the summation from k equals 1 to q of k squared. You understand? So this is the summation of the first q terms plus the last term, which is the q plus first term. Do you understand? What I'm saying here is the summation of q plus 1 terms equals the summation of q terms plus the q plus first term. What is the q plus first term? Well, the q plus first term will be q plus 1 subbed in for k. This is going to equal q plus 1 squared. Do you understand? What is the summation from k equals 1 to q of k squared? I'm going to use my assumption right here. The summation from k equals 1 to q of k squared equals this. So this becomes q times q plus 1 times q plus 1 all over 6. Look what I've gotten. This here is this. I have to now make this look like what? This, and I will be done proving. Well, let's see. I am going to get a common denominator between fraction 1 and fraction 2 by multiplying this fraction by 6 over 6, in which case I will get q times q plus 1 times 2q plus 1 plus 6 times q plus 1 squared. All of this is now all over 6. Everyone okay? All right. Now I'm looking here and I'm going to do, let's see, I'm going to do this. I am going to, let's see. Okay, I'm going to look at this numerator here, and I'm looking at this numerator, which is one term plus a second term. I notice I have a common factor of q plus 1, right? I'm going to factor q plus 1 out, and what I'm left with inside is q times 2q plus 1 plus 6 times q plus 1. Everyone okay? Right? All of this is all over 6, right? Now I'm looking at this over here. Look what I've got. I've gotten it almost there. I think what I'm going to do is simplify this up here. This is just the same thing as 2q plus 3, right? If I do that. Okay, good. Now, let's see. I'm going to, let's see, what am I doing here? I want to get to, okay, I'm gonna multiply this all out. Let's see, q plus 1 times, all right, 2q squared plus q plus 6q plus 6 all over 6. And then I'm going to make this q plus 1 is just waiting in the wings here. This becomes 2q squared plus 7q plus 6 all over 6. Oh, look, I have a factorable quadratic. Q plus 1, 2q, q plus 3 plus 1 all over 6. And I have just proven it because this is this. Okay, that's proof by induction. So now I have proved that for all values of n, the summation from k equals 1 to n of k squared equals that. That is proof by induction, which is a really interesting proof, a method of proof, because what you're doing is, if something is true for n equals 1, and you've just proved that's true for the q plus first term, what we've shown here is that when we know something is true for n equals 1, but if it's true for n equals 1, then steps 2 and 3 prove that it's true for n equals 2. Well, it's true for if it's true for n equals 2, steps 2 and 3 have shown that it's true for n equals 3, and so on and so forth. So that's why this proof method is sound. This method of proof is sound. All right, hope those of you who stuck through it enjoyed it, and I will see you for our question day in class on Tuesday, tomorrow. Sayonara.